let's do some microstate practice. So microstates are all the possible arrangements of a position and kinetic energies of particles in a system. So entropy of a system, as we've talked about before, increases with the number of microstates, because if there's more ability for them to be in a position, then there's more randomness in the system. So when using Boltzmann's equations, W, in this case, represents the number of microstates. S represents, as we've talked about before, entropy. K is then going to be what we've talked about before in the past. It's a constant. K is usually a constant. In this case, it's called our Boltzmann constant. So to calculate change in entropy, we need to know the number of initial and final microstates. Just if we had like initial and final volume, but in this case, we're just going to plug it into this part of our equation for W's on top and bottom instead of V's. So coming down, let's do a little bit of practice. So if we're determining our entropy change for the system based on this K and these pictures, remember we talked about this K just being what we are given over here as a constant, and then W final versus W initial. So it tells us that we initially have microstates at a distribution of 2. So I'm coming over to number 2. I see that I have 1, 2, 3, 4 microstates, and this is my initial. And then final, I have a distribution at 5. So I only have 1 microstate, which is my WF. So plugging all of this in, I have delta S is equal to my K, or my 1.38 times 10 to the negative 23rd joules per Kelvin, times my ln of my WF, which is 1, over my WI, which is 4, because those are my numbers of microstates at those particular distributions. And then the value that I get when I plug all of this in is negative 1.91 times 10 to the negative 23rd joules per Kelvin for my change in entropy.